Today we're going to be talking about doubling time and half-life. In your previous two videos, you learned about exponential growth models and exponential decay models. We're going to be using that knowledge. Example 1, Madison has 5,000 worms in her garden which multiply to become 7,200 worms in 10 days. How long will it take for her population to double? First, let's recall the growth equation. So we're going to have P of t equals P naught e to the RT. We don't know R. We're going to use what we know to find R. We know that P naught, our initial value, is 5,000. And we know that when time is 10, we have 7,200. We're going to plug this in. So we have 7,200 equals 5,000 e to the R times 10. And we're going to solve for R. So first, we're going to divide both sides by 5,000. We're going to get 1.44 equals e to the 10r. And now to undo the e, the base e, we're going to do the natural log of both sides. So we're going to get natural log of 1.44 equals 10r. And then we're going to get r by itself. So we're going to divide both sides by 10. And we're going to get r is approximately 0.0365. We're going to plug this into our equation now. So we're going to have P of t equals 5,000, our initial value, e to the RT, so 0.0365 t. This is our equation we're going to be using. Now, when is the population double? We know our initial value is 5,000, so double 5,000 is going to be 10,000. So we're going to be looking for what t is when we have 10,000 worms. So we're going to plug this in, 10,000 equals 5,000 e to the 0.0365 t. And now we're going to, I want this to be a little simpler so I can understand the numbers. So I'm going to divide both sides by 1,000 to make the number smaller. So we're going to get 10 equals 5e to the 0.0365 t. And now I'm going to divide both sides by 5. We're going to get 2 equals e to the 0.0365 t. And now we're going to take the natural log of both sides to get rid of the base e. So we're going to have natural log of 2 equals 0.0365 t. And to get t by itself, we're going to divide both sides by that 0.0365. And we're going to get t is approximately 18.99 days. And now we're going to work on one for half-life. Here's example 2. Iodine-131 is a radioactive material that decays according to the function A of t equals A naught times e to the negative 0.087 t, where A naught is the initial amount present and A is the amount present at time t in days. Assume that a scientist has a sample of 100 grams of iodine-131. What is the half-life of his iodine-131? So we're going to start off by plugging in our initial value, which is 100. So A naught is 100. We know that A naught equals 100. So we're going to plug this into our equation. So we're going to have A of t equals 100 e to the negative 0.087 t. So since we already have our rate, all we're going to need to do is figure out the half-life. So half of 100 is 50. So half of our half-life is going to be at 50. We need to find our time when A of t is 50. So we're going to plug in 50 for A of t equals 100 e to the negative 0.087 t. And we're going to divide both sides by 100. We're going to get 1/2 equals e to the negative 0.087 t. And we're going to take the natural log of both sides to get rid of base e. Natural log of 1/2 equals negative 0.087 t. And then we're going to divide both sides by negative 0.087. And we're going to get t is approximately 7.97 days. So it takes the half-life of iodine is iodine-131 is 7.97 days.